This is for exam 2. Jumping right into it, partial credit 1 starts by giving us the MIPS machine code instructions expressed in hexadecimal. We start by translating this into binary by using every digit in hexadecimal and translating it into 4 bits binary. Once we do this, we use the first 6 bits to figure out the opcode in the format. This is why we had to translate it into binary, because if we didn't, then it wouldn't split up into 6 bits, since hexadecimal is 4 bits. So the opcode is 001100, which translates into 12 in decimal, which corresponds to the opcode AND or AND immediate. AND immediate is a I format instruction, which means that the first 6 bits are going to be the opcode as usual. The next 5 bits are going to be RS. The next 5 bits after that are going to be RT. And the last 16 bits is going to be an immediate value. So, based on this, RS is equal to 00100, which is equal to 4 in decimal, which corresponds with the A0 register. RT is equal to 01010, which is equal to 10 in base 10, and corresponds with the T2 register. And the immediate is going to be 6 in decimal. And so this all translates into the instruction AND immediate, T2, A06. Partial credit 2 is solved in a very similar way, where we start by translating the hexadecimal value into binary, and then use the first 6 bits to figure out the opcode and format. So the first 6 bits here are 000100, which is equal to 4 in decimal, which corresponds to the opcode BEQ, or branch if equal. This is an I format instruction as well. So that means these 5 are going to be RS, these 5 are going to be RT, and this 16 is going to be an immediate value. So RS is equal to 01010, which is equal to 10 in decimal, which corresponds to T2. RT is equal to 00000, which is equal to 0 base 10, which is the 0 register. The immediate value is 18. So this all means that the instruction is going to be branch if equal T2 0 18. With question 2, we're asked to calculate the energy needed to complete the execution of the program. And based on these instructions, the program will execute one set instruction, which will need 6 nanojoules, 3 read or write instructions, which require 2 nanojoules, plus a loop that will be iterated 5,000 times, and this loop has 2 add instructions and 1 branch instruction. And these values are taken from the chart that's given. This will eventually simplify into 210,012 nanojoules, which is approximately 210 microjoules. Next, the question asks us to calculate the MIPS per milliwatt. So first, we start by calculating the clocks required for this program. So based on the program, we had 1 set instruction, which has a CPI of 6, 3 read or write instructions, which has a CPI of 18, plus a loop iterated 5,000 times, with 2 add instructions and one branch instruction. This ends up being equal to 110,060 clocks. Next, we need to calculate the time required to execute the program, and this is equal to the clocks required for the program times the clock cycle time. So this is equal to 110,060 clocks, like we calculated earlier, times 333 picoseconds per clock, which was given in the problem. This is equal to 36.65 microseconds. Next, we calculate the amount of instructions executed in the program. So it starts with 3 instructions that are not repeated, plus a loop iterated 5,000 times, and this loop has 3 instructions in it, and then there is 1 write instruction at the end. So this is equal to 15,004 instructions, which is also equal to 0.015004 million instructions. The reason we put it in this format is because we're getting into MIPS, or millions of instructions per second. So to calculate MIPS, we have million instructions per second, which, as we calculated before, was 0.015004 million instructions over 36.65 microseconds. This comes out to 409.386 MIPS. Next, we calculate the power using the energy needed to execute the program. So power is equal to energy over runtime, which we calculated both earlier, and energy needed to execute the program is 210 microjoules, and runtime is 36.65 microseconds. And this is equal to approximately 5.730 joules per second, or watts in other words. And so this is equal to approximately 5,730 milliwatts. Using our calculations from above, we can say that MIPS per milliwatt is 409.386 MIPS over 5,730 milliwatts, which is equal to 0.0714 MIPS per milliwatt.